In the second part of this video on object concepts, we will explain the difference between mutable and immutable objects and examine some examples in which whether an object is mutable influences the behavior of the program. Before we explain the difference between mutable and immutable objects, we need to begin by characterizing two kinds of methods. The first kind are accessor methods, which only access the instance variables of the class but do not modify them. Getter methods that return the value of a single instance variable are typical examples of such methods, but any method that does not modify any of the instance variables qualifies as an accessor method. By contrast, mutator methods are ones that do modify one or more of the instance variables. Setter methods that set a single instance variable to the value supplied as a parameter are typical examples of mutators. Keep in mind, however, that a mutator method may modify more than one of the instance variables. To reiterate a point made in the first part, making a habit of always defining a get and set method for each instance variable is not good object-oriented design, as we illustrated with the fact that a set method for the account class would be an example of a poor design. Having defined mutator methods, we can now explain the difference between mutable and immutable objects and classes. We begin by defining what it means for a class to be immutable. For a class to be immutable, objects of that class cannot be modified after they are created, which means that after an object is created, there is no way to change any of its instance variables. Examples of immutable classes include each of the wrapper classes, such as integer and character, as well as the string class. Although it may seem like strings can be modified by operators such as the concatenation operator, what really happens is that a copy of the string is created and the concatenation is performed on the copy, and the original string is not changed. Next, we explain what it means for a class to be mutable. There are three ways a class can be mutable, and any one of them is enough. First, having any public instance variables will certainly allow objects of such classes to be changed, since clients of the class can access them. Recall that we have previously mentioned that public instance variables compromise the practice of information hiding, and is therefore a poor practice in good object-oriented design. Having one or more mutator methods is the second way that objects of a class can be modified after they are created. So the presence of any mutator method makes a class mutable. The final way a class can become mutable is the most subtle. If a class has an accessor method that returns a reference to one of the instance variables of the class, and that instance variable is a mutable object, a client can retrieve a reference to such an instance variable and modify it. When a class has any of these three features, it means the objects of that class can be changed after they are created, so they are mutable objects. Now, let's look at an example of a mutable class, one that we will use in several of our future example programs. It is a wrapper class for integers. It differs from the predefined wrapper class integer, which is immutable. This class has two constructors. The first allows a capital I int object to be created from a primitive small I int variable. The second is sometimes referred to as a copy constructor. It creates a deep copy of an existing int object. For this class, we did provide both a get and set method. SetInt is a mutator method which makes this class a mutable class. It allows clients to modify the instance variable value after such objects are created. Scrolling down to the remaining methods, the final method equals performs a deep comparison of two int objects. This is in contrast to the equal operator, which will perform a shallow comparison. comparing only the object references. Unlike languages that came before it, such as C++, Java objects can only be allocated dynamically from the heap. That means that object names are references. As a result, it is important to understand the difference between shallow copying and comparing objects, which involve the references, and deep copying and comparing objects, which involves the actual objects pointed to by the references. When the assignment operator is used to copy one object to another, a shallow copy is made. So only the reference is copied, which creates what is often referred to as an alias, meaning two references that point to the same object. When a clone method or a copy constructor is used, a deep copy is made. In that case, we have two identical copies of an object. When the equal operator is used to compare two objects, it is a shallow comparison. A shallow comparison compares the references and only results in true when the object references are the same. Using either the equals method or the compare to method produces a deep comparison. So in that case, the objects themselves are compared, not the references. So typically, each of the corresponding instance variables must match. In some cases, equality is a bit more complicated. One example would be fractions that can be equal without being identical. A properly written equals method would take that into consideration. This program is intended to show the difference between deep and shallow copying of mutable int objects of the mutable int wrapper class we just discussed, compared with deep and shallow copying of immutable integer objects. Let's examine the declarations. We have three objects of type int. The first, int1, is created with the constructor that accepts a primitive int whose value is 1. The second, int2, is assigned to int1, which means a shallow copy was performed. So int1 and int2 point to the same object. The third object, int3, is created using the copy constructor that makes a deep copy of int1. So int1 and int3 contain the same values, but they are different objects. The next declaration creates three integer objects in much the same way. The first is initialized by instantiating an integer object supplying a value of 1. The second is a shallow copy of the first, and the third is a deep copy of the first. The first executable statement makes a call to the mutator method setInt and changes the value of int1 to 2. Then the values of the last two objects are displayed by calling the getInt method. Next, we attempt to do a similar thing with the integer objects. But recall that the integer class is immutable, so it has no comparable setInt method. So the only way we can modify the object integer1 is to assign it to a new integer object containing 2. After that assignment, the last two integer objects are output. Before we run this program, you may want to pause the video and try to predict what the output of this program is going to be to test your understanding of these issues. So now, let's run it. What you should note is that although we did not explicitly change int2, it was changed when we changed int1, because int2 is a shallow copy of int1. int3 was not changed, however, because it is a deep copy of int1. The other important observation to make is that with the immutable integer objects, neither of the second two changed when we modified the first one, because when we changed the first object, we assigned it to a reference to a new object and did not alter the original one. Now let's consider a similar program that illustrates the difference between shallow and deep comparisons of both mutable and immutable objects. In this program, we declare only two objects of type int, the second being a deep copy of the first. We do a similar thing with the two objects of type integer. Then we output the result of both a shallow comparison of the two int objects using the equal equal operator and a deep comparison using the equals method that we wrote. And next, we output the result of both a shallow and deep comparison of the two integer objects. Again, it would be a good idea to pause at this point and take the time to study this program and predict what the output would be. It will test your understanding of this concept. Okay, let's run it to see what the output will be. Notice that in this case, there is no difference between mutable and immutable objects, but there is a difference between whether we do a shallow or deep comparison. Because we did deep copies, when we shallow compare them, the result is false because the objects are different. But when we do deep comparisons, the result is true because both objects contain the same values. To further your understanding of this issue, try modifying this program to do shallow copies instead and see what the output will be. Our final topic in this part will be an examination of the difference in the behavior of mutable and immutable objects when they are passed as parameters. There is a common misunderstanding about how parameters are passed in Java. It is often misstated that primitives are passed by value and objects by reference, but that is incorrect. That misunderstanding arises from the fact that in Java, object names are references. In Java, all parameters are passed by value. Passed by value is a historical term that might actually have been better named pass by copy, because making a copy is what occurs. In the case of an object parameter, the reference is copied. The object reference argument is copied to the object reference parameter. By contrast, with a primitive parameter, the value of the argument is copied to the parameter. So with object parameters, the copy that is performed is a shallow copy. Because of the difference between what is copied, when a primitive parameter's value is changed inside a method, the change is lost upon return to the calling method. If, however, a mutable object is modified inside a method, its change is preserved upon return. In contrast, if instead of changing a mutable object's value, its reference is changed, that change is lost upon return. In a language like C# that does allow objects to be passed by reference, even changes to the reference would be preserved. Now let's consider our final example that illustrates these differences. In our main method, we have three variables. The first is a primitive int variable that is initialized to 1. In addition, we have two mutable int objects, each containing a value of 1. All three are passed to the method modify, and then their values are displayed. Let's see what the modify method does to each of them. The primitive value 1 is set to 2. The int object value 2 has its value set to 2 by calling the mutator method setInt. The int object value 3 is assigned to a new int object that contains a 2, so its reference was changed. As with the previous examples, take the time to predict the output Taking the time to predict the output is a good way to test whether you understand the difference between what will happen with each of these three parameters. So let's run it and see. Note that the change to the primitive parameter value 1 and object reference value 3 were lost upon return to main. They are both still 1. Changing value 2 by calling the mutator method setInt was preserved upon return. It has been changed to 2. It is important to understand that mutable object parameters behave differently from both primitive parameters and immutable object parameters. Mutable object parameters can be used to exchange information between the calling method and the called method in both directions. One final comment about the naming of parameters. In this example, the arguments and their corresponding parameters have the same names, but that is not required. Choosing 3 different names for the parameters would not have altered the behavior of this program. When a method is only called once, using the same name is fine. When a method is called multiple times, the parameters should be given more generic names, especially when the arguments differ on different calls.